Hi, and welcome to another episode of Nanotalks. This Nanotalk is a recording of a user webinar that we did with Dr. Xi Liu, who talked about iron-based heterogeneous catalysis research using our climate in-situ TEM gas and heating system. This webinar was hosted by me, Olaf Weller, and at the end you will hear some questions from our climate product manager, Ronald Marks. Now, my colleague, Dan Zhu, will introduce our presenter to you. So please enjoy this Nanotalk.
Hello, everyone. Now I will give a brief introduction to our presenter today. Professor Dr. Xi Liu did his PhD study on physical chemistry with Professor Dr. Robert Schlegel at the Fritz-Haber Institute of Max Planck Society between 2004 and 2008 in Germany. After graduation, she joined Professor Graham Hutchins' group at Cardiff Catalysis Institute in United Kingdom for 4 years. Later on, she visited the Center for Electron Nanoscopy in Technical University of Denmark for about 1 year. In 2014, she joined Syngas Chem BV in Netherlands as a research scientist, and then moved to SynCat at Beijing in 2015. SynCat at Beijing is the Synfield China Laboratory for Fundamental Research, which is dedicated to the science and technology for clean fuels from coal, based on molecular scale understanding. In 2019, she joined the School of Chemistry and Chemical Engineering at Shanghai Jiao Tong University, China. For over 15 years, she dedicates his research on dynamic, structural, and physicochemical evolution of catalysis under chemical environment with electron microscopy. He works closely with catalysis industries like Invista, Johnson Matthey, and Synfield China. As an electron microscopy expert, he also gains expertise on various catalysis topics like hydrocarbon functionalization, dehydration, biomass transformation, carbon chemistry, and so on. Now, she is continuing his research in the methodology and application of development of in-situ TEM on catalysis and electrochemistry in Shanghai Jiao Tong University. Xi, again, thanks for accepting our invitation, and now it's your time.
Great, thanks for this opportunity to give the presentation in this webinar and to share in some of the results presently I got by using the in-situ TEM technique. In this presentation, I will separate my talk in 3 parts. Firstly, I will talk about the reduction of carbonization and of the different treatment of iron catalyst. And later, I will introduce the new technology to visualize so-called atomically resolved surface morphology. And they will give the absolutely very different information from traditional environmental TEM, and it can help us to understand the active catalyst in more details. And finally, I will give the conclusion. So this presentation somehow I will not sharing so many successful stories. Somehow I prefer call the failure story. Then because I hope every people to know the difficulties when we want to use in-situ TEM to start our research. And I hope these difficulties can be realized and to be clearly explained, and they will help you to do the most reasonable design for your experiment. And hopefully, so it should be more important for the many people who start to use this new technique. I simply introduced the background of the heterogeneous catalysis research, but why we do that one? So every people knows heterogeneous catalysis that plays a very important role in the industrial synthesis, but mainly it's the noble metals that take almost 60% of the value of all the catalysts, heterogeneous catalysis. So in that case, people desperately demanded to use the cheap, so we call the base metals to replace the precious metals. Particularly, this metal has a high storage, more than the 100 years, 500 years, something like that one. During this so-called base metal catalyst like the copper, nickel, and also titanium or something like that one, iron is the most cheapest base metal catalyst and also has the highest storage in the world. And so how to use iron catalyst to replace the precious metal catalyst is always a very important task for the industrial catalyst. And somehow the iron catalyst already being used in some important areas. Firstly, is ammonia synthesis. This is one of the most important chemical industrial process to synthesize fertilizer. And they help the people to quickly develop the culture, the human societies, and boost the population from the 1 billion to almost the 6 billions doing the right now. And another experiment. This is a basic background of today's presentation. This is we call the Fischer drop synthesis. So somehow it's also one of the oldest chemical reaction. This is established in the 1970s in Germany, and we call the coal to liquid or the gas to liquid. Somehow so we use this technique to produce a liquid fuel instead of petrol oil. And this is quite important right now because some countries has a short of the petrol oil storage, and they can use a biomass, they can use gas to synthesize the liquid oil. And somehow the people also use iron to synthesize the biometric catalyst. However, this reaction is very interesting, but haven't been industrialized. And for the Fischer drop synthesis, this is a very complicated reaction. It's very different from CO oxidation and the water gas shifting reaction, and they got a lot of the product. And the carbon distribution ranging from the C1 to almost the C30. We always have some problems. So people like the very beautiful model of this reaction. This looks like the GFA image showing above. So we can see the carbon chain grows on the very beautiful and clean surface of the metal. And during the catalytic reactions, nothing changes. It looks like this. We can clearly understand what's active site and the different activity of the different area and how to dominate the catalytic performance. But somehow for the realistic catalyst, when we put the iron oxide inside, but when after reaction, we got out this different kind of iron oxide from the hematite to the wustite, and also different kind of iron carbide. So the used catalyst is just of the mass. They contain a lot of very different things and also impurity or something. So from the research point of view, so people always ask, can we see the undamaged catalyst? It means that the catalyst not so much different. They're working on the catalytic condition, and also further requirement is, can we directly see the active catalyst at a nanoscale and atomic scale, and to understand that how the catalyst, the activation or deactivation, and the working condition. The last, also maybe the most difficult question, is can we see the catalytic reaction? It means that it's not only the catalyst, but also the product and the reactant involved in the catalytic reaction. During this almost 100 years technique, the scientists developed the broad of the technique to have the different spatial resolution ability and have the different characterization analysis ability to see the structure and the chemical information, and to understand the recourse from the model catalyst to realistic industrial catalyst. So we know that we noticed that the TEM is on the very special position. They have very high, they offer the very high spatial resolution, and they can dissolve the structure information and physical chemical information. So if we can in-situize the TEM and to put the gas inside and to keep the spatial resolution unchanged, And we can also capture the dynamic changes immediately, like the video showing that way. It looks fantastic. We can see this catalytic reaction and happen on every facet, every corner and step. And look like we can directly understand the catalytic reaction. Is that is real? But somehow, unfortunately, it's yes. Use this technique, we definitely can see the non-contaminated catalyst. It means that if it's we treat the catalyst in a very careful method, the catalyst will not be contaminated by the oxygen and the outer atmosphere. And we can see the catalyst and just remove of the chemical environment to understand what's before and after reaction. And definitely we can see this structure evolution of the precursor and the catalyst on the reaction condition at the nanoscale and even sub-Armstrong scale. This is fine. But to be honest, we cannot see the catalytic reaction at all. So somehow this technique is not technique all in one. This is a technique we use to examine the catalyst onto the active atmosphere instead of to see the catalytic reaction directly. So they give the information is very useful, but also limited. So why the reaction is very limited? Because also we have the limited knowledge about the catalytic reaction. The above, this is a Fischer-Tropsch synthesis. So the left side is a kinetic of the Fischer-Tropsch synthesis, but the right is kinetic of the activation of the catalyst. So we can see that something is very different. The catalytic reaction happened on the different facet and on the different step. We can use theoretical calculations to understand the energy of the intermediate compounds. But by using catalytic, by using in-situ TEM technology, we directly see the activation of the catalyst, not the catalytic reaction. This is something happened at the atomic scale. We want to see that one, and we want to use this technique to get this information and try to help us to establish the structure-activity relationship. But the situation is more complicated. It's something like we want to use this technique to visualize this kind of information. This is activity related with the special active sites about the corner and the edge and the bridge or something like that one. But in most cases, the catalyst are viewed in the institute here is look like this way. This is catalyst has several dozen nanometer to 100 nanometers, and they have the pores, channels, and the defect. And in that case, the diffusion and diffusion of the reactant inside the catalyst and absorption and the many different chemical process dominated influence the catalytic reaction heavily. And in that case, we cannot use that one to examine the fundamental catalytic reaction step. But most worse is the last one. So the people come here to examine, want to use the in-situ technique to do the research. It is because they found something very interesting in the fixed back reactor. And in that case, several gram catalysts put in the reactor. And they found that they showed a very beautiful catalytic performance. But in that case, what dominates the catalytic performance is even not the diffusion, is really heavily related with the mass transferring and the thermal transferring. Just hold on. Yeah, okay, sorry. So if we separate these three levels, the scientific problem, because the thermodynamic will not be changed, even without catalyst, the thermodynamic would be the same. But the kinetic is very different. In the fixed back reactor, we always call a macrokinetic. And when we focus on the single particle with the size of the several nanometers to several hundred nanometers. We call the macrokinetic or intrinsic kinetic. Intrinsic kinetic is often related with the fundamental reaction step. But here we want to distinguish the macrokinetic and the intrinsic kinetic, because when I use in-situ TEM, I found even by using the catalyst with several hundred nanometers, that is very different from the fixed pack reactor, but we also has a very different kinetic problem from the intrinsic kinetic. So I want to separate these three things and give the explanation how the macrokinetic dominated the catalytic reaction happening inside the in-situ holder, and when they strongly manipulated the performance and give the very complicated chemical view behind the reaction. Here we give the example why the fixed pack reactor is not so reliable. We can see that there's a temperature distribution is very different from central part to the wall of the reactor, and inside the reactor, when you use a different shape of the catalyst, you can see that the mass distribution itself is also very different. That means that in that case, for a lot of the industrial process, the mass transferring and the thermal transferring dominate the performance. And we can see that here is a parent activation energy for the catalyst. Same catalyst operated at a different condition. You can see that on the macrokinetic condition, the diffusion dominates everything, and this is very different from the intrinsic kinetic information. During the 1914 and during the 1914 to almost the 2014 and 2019, I work in the same field China. So this is one of the biggest company working on the fish chop synthesis in China, and they build up a lot of the big plants in China. They generally focus on the use the cold to liquid technique. So in this company, we want to understand how the fundamental chemistry behind the iron activation to become for the fish chop synthesis. So in that case, we bought almost the first the climate instrument from Dan Solution in the 2017, and we installed it immediately. And this is just to show how the instrument working. So by using the instrument, we can directly introduce the gas inside the TEM and raise the temperature from the room temperature to almost 1,000 degrees, and manipulate the pressure of hydrogen from the several millibar to 1 atmosphere. So we observe this how the reaction happens from the iron oxide and to the active catalyst iron carbide, and also suffering some of the deactivation to the magnetite. So the most successful story is that we use this technique to carburize the iron to iron carbide. But this part of work I will introduce, but just with several pages of the PPT. Mainly, I will talk about this story. Oh, sorry. The iron oxide to iron. So this reaction is very simple, looks very simple, but by doing this reaction, we found a very complicated chemical view. And this information can only explain it by the macrokinetic things, not thermodynamic thing. And this complicated thing also can help us to understand a lot of the fundamental science behind this one. And this story is not so successful because we have to use extremely critical condition to get the iron. So this condition is not so favorable for the industrial process. But finally, we got some good information, and I hope this information can raise your interest to understand the chemical reaction related a lot of the reduction of the metal oxide. And based on the diagram, phase diagram, we can show here. This is iron oxide reduction by the CO and hydrogen form metallic iron. So based on the diagram, there's a phase diagram. The information is looks very simple. Even at 300 degree, we use pure hydrogen, and we can get the reduction, completely reduction from iron oxide to the hematite to the metallic iron. But somehow, if you see the reality here, when we use a different temperature from the 200 degree to 800 to almost 1000 degree, we can see the reduction of the iron oxide to the iron is very difficult. At the low temperature, about 300 degree or the 200 degree, it will take the several dozen hours or 100 hours, and you cannot get a complete reduction. This is very different from this diagram. And even you reach the temperature to about 952 degree, you can see that you can get a quick reduction from the real 0 degree to about 80 degree, 70 degree. But afterwards, reduction is very difficult and it takes a very long time to do that. And if we use a reduction degree to calculate the activation energy, we can see that the iron oxide reduction activation energy changed at a different temperature. So it's suggested this process is strongly determined by the kinetic, it's not by the thermodynamic. But what happened and in the different reduction process, and how to visualize this kinetic process? So we have to use the new technique to do that one. In this case, we use the in-situ TEM to do this work. So that's also some very interesting thing, and you can see that they have this kind of S-shapes the curves for the reduction process. It means that by using the different particle size and by using the different heating ramp, the reduction rate is also very different. So somehow, based on the reduction of the iron oxide by hydrogen already been started almost the 60 years or 70 years. Based on the experimental result, people suppose that on the different stage, the several different mechanisms dominated. For example, at the low temperature, they call the diffusion process, and at the mediate temperature, people said that they have the limited mixture control mechanism. On the high temperature, they have the uniform internal reduction process. But however, people didn't give the very beautiful image about how the reduction happened at the different processes at the real realistic reduction condition, and also as with high spatial resolution. Also, another problem we have to consider, this is rarely discussed in any reference, is about the penetration of the hydrogen. Penetration of hydrogen inside the metal has been well known for the construction, because for the metal and for the construction, because it will cause the hydrogen damage to the metal and to the instrument. But this information has never been considered for the hydrogen reduction, because always people think the diffusion rate is diffusion of the hydrogen inside bulk is very slow, but somehow it's not. Based on the calculations, the diffusion rate is quite high, even not in the metal, but in the metal oxide, the diffusion rate is still quite high. So they will play some important role for the reduction of the iron oxide. Here we are based on the reference of my work. I proposed the reduction of the iron oxide to finally to the metallic iron. They suffer in the different step. In the middle step, this is dominated. It's not dominated, but this influenced by pressure. We can see with high pressure and with low pressure, the phase transformation is very different. And they suffer in the two steps. They call the physicochemical transition step from the iron oxide to the magnetite. But with high pressure, this is generally dominated by the nucleation and the diffusion. And afterwards, the last step from the magnetite to metallic iron is less influenced by the pressure. This is very strongly manipulated by the kinetics, and they cause finally the production of the metallic arrow is generally from the nuclearization process. And this work, published in the 2017, get very beautiful image about how this topochemicals transition from the hematite to magnetite. They use a very low pressure, is 0.2 Pascal of the hydrogen in the TEM to visualize this process. And in my experiment, I reproduce this result, but use a 2.5 millibar, it's almost 1,000 times higher than this one, at 500 degree for the reduction process. This is happened at 500 degree. So it looks like this process is very different from this paper published in 2017. But if we take the central part of this one, we can see in some part, the reduction is also happening in the topochemical reaction. There's directly transformed from hematite to the magnetite. And but we notice the different part, the situation is very different. We can see the growth of the hematite particle out of the parent material. And this particle is very mobile and just dispersed all around of your chips. This looks like, although the topochemical transition can happen under some reaction condition, but somehow the deformation, the degradation of the iron side in present hydrogen is some predominant process during the reduction. If we see completely the transition process happened on the one bar at 500 degree, we can see initially we see the iron particle didn't change a lot, but during the reduction process, there's a new phase diffused out of the parent particle, and afterwards, the inside particle suffering the strong reconstruction process, and a lot of the new, and even we can see some explosion happened inside the particle. And during the reduction process, we can see the nuclearization of the magnetite happened at the corner. It means that the new species of the iron oxide immigrate from the parent particle to the corner and form the new particle with a different crystalline structure. Here is another particle, and they can give the more clear information about how the deformation and the deconstruction happened with a very high hydrogen pressure. And it's very interesting to see that something happened inside. It means that there's a structure incapability due to the induction process happened. And if we see the initial reduction process, the new spaces formed and diffused out of parent material, but they have the identical crystal structure to the parent material. And this is a TEM images and STEM images. We can see the diffusion phases during the reduction process happened. And this new form phases is still the hematite. But when we use yields, we confirm that this hematite is partially reduced. This has happened because this hematite is partially removes the oxygen, and then the deformations happened following the reduction process. But at this stage, the complete reduction from hematite or the magnetite didn't happen. So in that case, we can see that when this process is completely dominated by the hydrogen diffusion and the penetration, and the deformation and the degradation happened at the high pressure, it means that at the atmospheric pressure. But the interesting thing is, even we increase temperature to the 750 degree, and we cannot get any formation of the metallic arrow. So if it's compared to the phase diagram, the condition is extremely high, but the reduction is very, very difficult and to get metallic one. And this is process. So we both use the in-situ TEM and the in-situ electron diffraction technique to examine how the reduction happened below the 800 degree. We can see the particles suffering the strong reconstruction process and the growth of the new crystallines, the magnetite particles with a very beautiful particle shape. But during the whole reduction process, the iron didn't form below the 800 degree. And this is the final picture we got it, and at below the 800 degrees. So we see that we got the octahedral shaped the magnetite particle, but no iron formed. But what happened to the further when we increase temperature to higher to the below the 800 degree, and how the reduction of the magnetite? And we found the very interesting information. This is a reduction of the octahedral magnetite at about 850 degree. And we see this more patent and change during the reduction process and change periodically. And this is FFT of this nanoparticle. And we can see the very interesting the periodical change in FFT pattern and during the reduction process. If we look at this point, and we can see this structure changed, and this modulated structure changed during the reduction process. So clearly, there are some things, the new species formed on the surface of the octahedral iron oxide magnetite nanoparticle. And due to the overlapping of the new species and of the magnetite, and the more patterns changed. But this reduction process changes periodically. So once this new species was removed out of the octahedral magnetite, the pattern changed back. If we just choose the pair of the pattern to do the IFT, and we can clearly see how the surface reconstruction happened, and give the very clear information about how the bark and the surface changed during the reduction process. And we found this things happen generally for all kinds of the iron oxide nanoparticle. Because this surface reconstruction, because it's an overlapping problem, so if the magnetite don't have the very good shape, also not in the right orientation, we cannot see it at all. But if we can get this octahedral particle in the right direction, we can see the same reconstruction process on the surface. And this suggests that the formation of the new species cover the surface, and afterwards is removed by the reduction process, during the reduction process. So this is the octahedral particle. And during the reduction process, it looks like hydrogen penetrated inside the surface and formed the new species completely covers the octahedral magnetite nanoparticle. Depending on the diameter change during the reduction process, the thickness of this new species is around about 2 nanometers. And later I will give evidence to show that why our spatial assumption is right. It is quite interesting. If it can correlate it to the reference, the Professor Ertel discovered this is the spin, the spirals, the movement during the catalytic reaction. And it's supposed that because the hydrogen and the seal penetrated on the subsurface and caused the reconstruction process. And recently, the Dr. Zhu Junwang and Mark Willinger published a very beautiful image, the paper, to show this. They use SEM to visualize the spirals, the movement on the surface of the precious metal. And we can see this periodicals changed during the catalytic reaction. So this situation is quite similar to what we see in the reduction of the magnetite. But this is quite an irreversible process. So somehow we do the other experiment like the cobalt catalyst to do that one. We found this under the different chemical, under the redox reaction condition, the cobalt is quite mobile under reaction condition. So this is prove our assumption is the penetration of hydrogen into the surface and cause the reconstruction somehow dominate the second step, reduction of the magnetite to the atom and the penetration. So we get other evidence. So we somehow use palladium as subject to study how the hydrogen penetrated in the metal and from the metal hydride, because the palladium hydride is quite stable, so we can use different techniques to examine it. And in this paper, and done by the Professor Vincent Zhang, we use EOS and in-situ XRD technique to examine this one, and found that really the hydrogen can penetrate it in the palladium nanoparticle and form the hydride. This is kind of evidence we can support our examination. But when we increase temperature to even higher, to almost 900 degrees, we see the formation of the metallic arrow. But still, the magnetite is very difficult to reduce it. As with collaboration with Thomas Hansen, we do both the in-situ diffraction, electron diffraction technique and in-situ TEM, in-situ XRD technique. And we found the reduction process is really difficult at below the 900 degree. We really need an extremely long time to get a coupling reduction. But what hinders the magnetite reduction to metallic arrow is still not clear. So now we have the last question, is we found the mixture of the iron and the iron oxide, but the iron is formed on the surface of the iron oxide or the different places. This is Hardy STEM images, we got this one. Based on the STEM images, we cannot get the clear information about this one. But in that case, we use another new technique. It's called the atomic reserved surface technique, the secondary electron technique. To do that one, they found very interesting thing. This is a big iron particle formed inside the bark of the magnetite, not on the surface. It suggests that the diffusion is not the rate determining step for the reduction, but other process. So they suggest that we guess the water maybe plays a very important role to stop the complete reduction of the iron oxide to iron. But presently we don't have other evidence to prove that one. So last one, this part I will quickly story about. When we get the iron, we can do a lot of things. For example, we can do the carburization of the iron to iron carbide, and we can get to examine the dynamic reconstruction process from iron carbide, and to even we can see how the carbon formed from iron carbide, and then we can see this. Then we can also use that one to re-examine the oxidation of the iron oxide to oxidation of the metallic iron to iron oxide. So we also found quite interesting thing is the oxidation of the iron oxide is also determined by the pressure. So at low pressure, at low pressure, we can see the formation of the iron oxide is a nuclearization process. We can see gradually formation of the iron oxide on the surface of the iron particle. But with high pressure, it's very interesting. We can see definitely the reaction rate is very fast. But we found during the oxidation process, we found the co-shell structure. It suggests that the oxygen penetration or diffusion inside the surface of the bark is very different. So here we quickly give the conclusion about this one. We saw the very different behavior at a different temperature, and they give the very important information, tell us how the kinetic or macrokinetic dominates the reaction process, and how can we correlate the macrokinetic with the morphology of the iron oxide at a different stage and give some information. But the story is not completed yet. And here we talk the second part about atomic reserved surface technology. We know that the surface technique is very important for the heterogeneous catalysis research. And this is because the TEM is very powerful technique, but somehow it is a 2D projection technique. It's very difficult to differentiate the surface information and the bulk information. And this sometimes causes the misleading result. And recently, the IMAT used the in-situ holder produced by that solution, and due to the 3D reconstruction process, 3D tomography technique to visualize the nanoparticle at a different direction stage. And this is very important and very beautiful information to tell us how the catalyst is working on the surface of catalyst working on the real reaction condition. But here we use another very different technique. This is embedded in the Hitachi TEM called HF5000. They put the secondary electron detector inside this e-stem. So in that case, so firstly, with this technique can introduce the gas inside to do the environmental TEM work. But also they have a secondary electron detector, so they can get the very surface information, help us to understand the topography of the catalyst and about the surface. So this is a good example to show how we found the position of the iron. So iron is not on the surface. It means that hydrogen can easily diffuse from the iron oxide into the bulk and reduce the iron oxide to the iron. And also suggests that the reduction process is not because of the coverage of the iron stops the diffusion of the iron oxide. And we check the different particle. We always found this big particle found is inside, beneath of the iron oxide. It's not always on the surface of the iron oxide. They give the very different information from the later reference. But if we give the high resolution image of the secondary electron, we can say iron particle. This is a magnetite particle. The surface is very complicated. And we can see with higher magnification, and we can correlate this octahedral particle shape with the TEM image we got in this one. They prove that our observation in the in-situ TEM is right. When we increase the magnification into the even higher, we can see the step, and on the surface, the thickness of step is about 2 nanometers, and this is correlated in good agreement with our assumption during the calculations. And also we can see here from the dark image, we can clearly see the image of the metallic arrow, but from the secondary electron, we cannot see the particle. It means confirm this particle is at bulk. And here is a very interesting image. This is even higher magnification. It's about 2 million magnification. This is a dark field image of the nanoparticle found in situ under the hydrogen atmosphere. And we can see the lattice from the dark field images. But here, this is secondary electron images. They suggest the iron oxide surface have a very complicated feature during the reduction. And these features could be related to this reduction behavior. So as I say, the TEM is not technical all-in-one. So in the Shanghai Jiao Tong University, we are going to build up a so-called in-situ center for physical science. We want to put a different instrument with in-situ function together, so we can visualize the same target with a different spatial resolution and with both the physical structure information and physicochemical information at the same time. I hope it will greatly help us to understand heterogeneous catalysis and other research. So here, thank you much for your attention. The presentation is a little bit long. And thank you for my collaborators and for the financial support from the NFFC and the CPU China and the Shanghai Jiao Tong University. Thank you very much.
Okay, and we from Dent Solutions want to thank you very, very much for your great presentation. And I hope everybody was very interesting and inspirational for everybody. So now I want to, before we go over to the questions of the audience, I want to first ask my colleague Ronald to ask 1 or 2 questions to see.
Yes, thank you. It was really a very super interesting presentation on all your research relating to in situ, Professor C. Also on what is going on for both for synfuels and on the Jiao Tong University in Shanghai. So once again, thanks for preparing this preparation for this audience. Regarding the questions that I had, so you showed us several methods to do in situ gas and heating experiments. One, of course, is using a nanoreactor, as we do with the Climate G+ system. But alternatively, people are also still using TEM with a large specimen chamber, which is filled with gas. And you also showed the Hitachi system, which is more of an open cell type, where you inject gas into your on top of your sample into the specimen chamber. Maybe you can tell us a little bit more. Do you have any preference of method for your in situ experiments, and where does one method is better suited for a certain type of experiment?
Yeah, thank you very much for this time to share my experience. Somehow I think that whatever the ETEM or ESTEM, they have the very powerful function, and they can guarantee the reaction condition at the low pressure. But when we want to examine our reaction related with a different pressure, we have to use the in situ holder to do this experiment, because the in situ holder can increase temperature to really high, to about 1 bar or 2 bar. So this is very necessary for many catalytic reaction. And we know here, we show some examples, the catalytic reaction is really pressure dependent. So we now know the advantages of the in situ holder. This is the first advantage of the in situ holder. And also other things like we can quickly manipulate the gas composition, and we can ignore the contamination of the in situ reaction to the TEM. And they also greatly help the people to design their experiment and to do the in situ TEM very easily.
Okay, thank you for your explanation. I have a short second question, if that is allowed. So yeah, you showed several reduction experiments using hydrogen gas, also some with carbon monoxide and methane. Are you planning to use any other gases in future experiments for your in situ research?
Yes, we do a lot of things. We do the oxidation, we do the carbon combustion, and we do the carburization experiment using holder, and we produce a lot of results. And later on, if opportunity, we want to share in this one. The one thing I have to mention is that one. And initially, we ignore the difficulty of the reduction process. We think it will be very easily achieved it. But later on, we have to increase temperature to 1000 degrees. Then we can get the complete reduction of dioxide to air. At this time, we will worry about the stability of the in situ holder, and we don't want the breakage of the holder cause the damage of the TEM. But finally, we surprisingly found the holder is very stable and the chip is very stable. We easily increase temperature to 1000 degrees, and we conduct this critical reaction condition for almost 1 hour or 2 hours, but we didn't see the deconstruction of the chips. And this is a very good experience when we do the in situ reduction process.
Okay, yes, indeed, it is still a phenomena which is not very well understood, why this reduction doesn't take place in the nanoreactor at these high temperatures. So there are also other researchers that reported on that. Yeah, we will keep working together and be in contact about this, and then try to find out more what is causing this strange phenomena. But thank you for your answer, and we can continue with the Q&A, Olaf.
Yeah, thank you very much.
Okay, well, we have 2 questions of the audience that we will handle before closing off. So the first question is, in your in situ study, what CCD camera do you use?
We use a different CCD camera. I mean, for the in situ holder, we use a CETA. We use a CETA camera to record the videos or something like that one. We haven't used, but in some cases, I use a one view camera from the Catalysis to quickly visualize the oxidation process.
All right, thank you for your answer, and hope that answers the question of the person who posted it. And the last the last question of the attendees is in slide 39. Maybe you can go back to slide 39. During oxidation experiments, what oxygen pressure and temperature were used?
Yeah, I didn't mention very clearly here because it's quite fast. So the temporal chemical oxidation happened is below the almost 0.02 Pascal. So it's with an extremely low oxygen partial pressure, you can see the temporal chemical oxidation process. But the ultra high oxygen pressure, this is why it's quite high. It's about from the several millibar. And you can see the explosion of the iron by the oxygen. But the medium level of the oxidation, this is a nuclearization process, maybe happened about the several Pascal. And but this is really depend on the temperature. That means that at the lower temperature and with high pressure, it will can happen. But with a high temperature, like the 600 degrees or something, the oxygen pressure should be quite low.
Okay, well, thank you very much for clarifying that. And with this, I want to give a big thanks to you, Xi, for your great presentation. And any closing words?
Yeah, so thank you very much for this time to sharing this one, and hope that later on we can discuss the more details. That there's an email or other method. Thank you very much, and also thank you very much for the dance solution for this opportunity.
Okay, and my colleagues.
Okay, well, thanks very much everybody for attending, and hope to see you soon next time.
Thank you, Xi, for giving this presentation, and thank you everyone for attending this webinar. Thank you.
Okay, and with that, we come to the end of this Nanotalk. Thank you all for watching, and I invite you to follow us on our social media accounts, LinkedIn and Twitter foremostly, and also subscribe to our newsletter so you will always be informed if we will organize new webinars. And well, this was it. Thank you for watching, and see you soon.